Okay, so welcome to day number 2. Welcome back this morning. I hope everybody has been able to get around and find lunch and everything as well as possible. So I'm very happy to introduce Romit Maulik from Argonne National Lab. Romit is you may be getting your clicker.
I think there was one yesterday, and I think this might be the one you're looking for.
Okay, wonderful.
So what should I do
so Romit is an assistant computational scientist at Argonne. Actually, we've had him visit us here on campus for a few occasions, and we're excited to have him back today for the summer school to talk about nonlinear dynamical systems and learning from data. This is an enormous area of research in a variety of domains, and Argonne, especially with its leadership class computing facilities and amazing scientists, is doing really great things. So please join me in welcoming Romit. Thank you.
Okay, thanks everyone. It's been a while since I've been on stage, so I'm trying to deal with the stage fright a little. But thank you everyone for being here. Thank you to the organizers for the invitation, for the introduction. As was just said, I'm a staff scientist at Argonne National Laboratory, but Argonne is a really remarkable place because it's situated in the middle of an ecosystem which has a lot of great universities. So we also have extensive engagement with academia, and so are highly interested in not just problems that run on supercomputers. That is the general impression of many of the national laboratories. So hopefully some of the work I speak about today can enlighten you about the things that we are interested in. So this talk I've kind of designed it to be somewhat of a tutorial. So this is a summer school, and I'm sure if someone speaks for 2 hours and basically fire hoses you with jargon and terminology, you may not end up taking a lot away from it. So, but at any moment, if there's any questions, please feel free to interrupt me. And I'm going to be around all day today, so happy to chat more. But this is going to be an overview. I also have some code that is available at this GitHub link that's up here. Feel free to go check it out. If we have some time, we'll walk through it. But again, the code has been written. I mean, I don't want to brag about my code writing skills, but I'm sure someone will take offense at something I've put in there. But you can go in there and take a look at some of the things that we are trying to discuss today. Okay, so this is the outline of my talk today. So of course, I'll start with a little bit of a motivation, a little bit of an introduction as to why we do the things we do. And then since we talked about dynamical systems, we look at a couple of strategies for learning both deterministic and stochastic dynamical systems. And although I have a Q&A session at the end, please feel free to have the Q&A whenever something interests you. Okay, so let's get started with the motivation. Okay, so I talked about Argonne being the home of certain very large computers. It's a privilege to have access to them without having to write large grants. So some of the ways we may take advantage of these systems are by running extremely large simulations. For example, on the left is a simulation that I'm running with some collaborators over here using a code that is developed not just at Argonne, but at other national labs as well, called E3SM, the Earth Energy Exascale climate model. And what we are doing for the first time over the last year or so is actually resolving clouds in climate models. So historically, whenever you've seen results from climate models, with the Earth warming or cooling, clouds were never, present in your climate models because you needed to have grids that were coarse. So cloud is a certain structure on a particular scale. But now we are starting to resolve them. Why is this important? Because clouds reflect sunlight, and the amount of reflection they do actually determines how the planet may cool. Clouds actually have a cooling effect. So on the right, there is a simulation that was run actually at Oak Ridge National Lab by some folks at ECMWF, that's the European Center for Intermediate Weather Forecasting. This was a weather simulation, which was run on a 1.4 kilometer grid. So, we're starting to reach simulation sizes where neighborhoods, cities, et cetera, are getting resolved. So there is a tremendous amount of data that is being generated. And as you can see, the simulation that they ran, which was actually the plenary of Supercomputing 2020, was very well validated by an actual satellite observation of a particular day. So we are starting to get really predictive. But you can see some of the numbers that are being that I've put down over here. So for example, the E3SM runs that we are currently running on Theta, our supercomputer, require 120 million core hours of compute. That's a lot of greenhouse gas emissions, basically. Okay, that's and when Aurora comes online, which is slated to come online 2021, which is going to be one of the largest computers in the world, the power consumption of Argonne National Laboratory is going to double. Okay, it's like adding a Naperville-sized power consumption to the lab. So what we have is a requirement essentially to look at all this data and from my background to see how we can learn these dynamical systems without having to go back to the high performance computer so frequently, right? Add machine learning and data science as a component to your computational tool belt, so to speak, so that you end up saving a little on these large simulations, which are always going to be necessary. But we want to see if in the process of scientific discovery, we can reduce some of these costs. Okay. And so we go back to a paradigm which is not really new. So my background is aerospace engineering. And in the aerospace and mechanical engineering community, surrogate models have been around for many, many decades for the purpose of what we call outer loop optimization. So the idea over here is that if you have certain design parameters in your system, it could be dynamical or static, you can, of course, incur an offline cost to generate some simulations of these data. Frequently, if you're lucky, a lot of these simulations may be available to you in the form of public repositories, which in the climate community is definitely, is definitely true. Once you have those data sets, which you have over here in the top loop, you can actually build a data-driven alternative pathway from your design parameters to your outputs by using what is now called training, but back then it was, we called it, for example, response surface fitting or kriging. So different types of strategies may be used over here. And so once you have this surrogate model, which by definition is assumed to be many orders of magnitude faster than your original simulation, you can then use it for a variety of things, such as sensitivity analysis. So if you perturb your inputs, how much does your output vary? Optimization, so finding a desired design parameter given a specified output. And of course, risk analysis and so on and so forth. So control. There's a lot of things you can do if your forward model is actually cheap. So the idea is, can we leverage this expertise in surrogate modeling that has been around for a while, and of course couple this with these very, very large or very, very computationally effective modeling strategies that are around because of the GPU revolution to learn systems that are relevant to, for example, weather and climate forecasting. So over here, for example, one requirement that we add in addition to the fact that we want to build a data-driven system is that we want to not make any assumptions about the underlying nature of the equations. Okay, so when people traditionally build surrogate models, the idea was that you would have some knowledge of the system. So if it's a fluid flow system, you'd say that it's coming from Navier-Stokes or some variant of a F equals ma type equation, and you'd build that into your surrogate model. So to give you an example, let's say you have a PDE, you find a coordinate transformation for your PDE, so that you now have a reduced system which becomes something like an ODE, which is very, very easy to solve, very, very quickly evaluatable. But for a lot of systems, for example, the simulations that I was showing you, you have extremely incomplete information. So at present, the equations you write down for something like the evolution of the sea surface temperature, or which we'll look at today, or for example, how clouds are formed in a 100-year climate simulation are rudimentary at best. So these are avenues for us to actually learn systems that may beat, in terms of accuracy, the equations that scientists have put down so far. Okay, so and that type of reduced order model or a surrogate model is considered non-intrusive. So you have an intrusive reduced order model and a non-intrusive reduced order model. The idea of a non-intrusive reduced order model is you look at data and you build a reduced order model or a surrogate model from that data, but you make no assumptions about the underlying equations. Okay. What we would like to do is we would like to build these models and also extract some knowledge of what equations they may potentially be under the data. Okay. All right. So the first part of my talk today, the first R, is work that has been done at Argonne, Los Alamos, the national labs, and also some collaborators at Wisconsin, Carnegie Mellon, and we'll be looking at a variety of tasks over here, but the overarching sort of theme is non-intrusivity. So data that is available to you, potentially poorly resolved both in space and time, and you make no assumptions about the underlying PD. In this case, these are all PD data. Okay, so let's look at a few background technologies before we go in and start learning these systems. So you may have been familiar with the machine learning literature recently. So in 2018, there was this paper that won the best paper award in Europe. So it was called the neural ordinary differential equation. It was a little surprising to a bunch of us in the old-fashioned dynamical systems community, because this idea has been around since the early 90s, about basically having an equation 1 given by a unsteady term on the left-hand side being parameterized by a neural network on the right-hand side. So this has been around for a very, very long time in optimal control. This has been around for a long time in equation-free modeling. So, Dr. Yanis Kevrakidis at Johns Hopkins actually published a paper in a chemical engineering journal, which has only 20 citations today, I think, where he did basically exactly the same thing that the 2018 paper on neural ordinary differential equations did, without GPUs, of course, back then. The neural ordinary differential equation paper, I don't know, has 10,000 citations or something right now. So just letting you know that good literature review always pays dividends. So but what is undeniable is the fact that with large computing resources that are available nowadays, a lot of these ideas that were somewhat unfairly investigated and discarded in the early 90s are coming back to prominence and actually giving us some rather phenomenal results. So it's a good time to look back and do a thorough literature review, I would say. I think very important. Okay. So what is the neural ordinary differential equation? The idea is very, very simple. If you've taken an intro to ODEs type course, like I said, you have an unsteady term for a system which is given by a state A, and on the right hand side you have a function of A that acts as that basically propels A through time. Our idea is that if we have examples of A over time, right, this could be unevenly distributed in time as well, can we actually learn the right hand side? Okay. So what has commonly been done in reduced order modeling or in the engineering community and surrogate modeling generally is to look at snapshots of a dynamical system and build this sort of map, the flow map, for example. What people have done is they've usually specified what F is on the right-hand side. So from some best guess estimate, let's say F has a diffusive term, it has a advecting nonlinearity, they'll specify these. And in the process of that specification, of course, you get interpretability, but you also perhaps have too strong a prior, to use a Bayesian sort of phrasing. So sometimes your best guess of the dynamics actually causes you to be poor in your accuracy. So what we do over here is we take a step back and we say, okay, for now, let's just learn the dynamics properly, and then moving on, let's try to infer what features of the dynamics we can actually extract. So, for example, I will have a couple of examples today where we look at chaotic systems, we look at advective systems, and we'll see that with the technique that I will introduce in the next slide, that we are actually able to first learn the dynamics and then extract some structure from the system, which is the whole concept of scientific discovery. Okay, so very quickly, how does the neural ordinary differential work? How do you know what the parameters theta on the right-hand side are? The idea is you use your personal favorite OD integrator, right? There's so many. You specify theta randomly initially, and you basically integrate one in time to get a loss, right? It's basically a divergence of your initial trajectory with your actual training data. This loss is then back propagated, which is again machine learning terminology, but you solve the adjoint of that loss, which is another ODE system that is solved backward in time using equation 3. By the way, equation 3 is nothing but a continuous analog of the discrete sort of backpropagation algorithm that is there in a like a standard feed-forward neural network. And so with equations 2 and 3, you call one forward solve, one backward solve of the adjoint, and then you can get the gradient of the loss, the divergence of the trajectories, the trajectory coming from a garbage choice of theta and your actual training data. And you can then put this into your choice of an optimizer and improve the theta. So at the end of the day, your hope is that you get a right-hand side that is similar to what might have generated the training data that you observe. Okay, so instead of going into further numerical or algorithmic details, I figured we should just start looking at an example right away. So the first example that we'll be looking at is the Kuramoto-Shevasinsky equation. So this is an equation as given in equation 5 and 6. This is a very interesting problem and is looked at by a lot of people who are doing turbulence modeling, climate modeling, combustion modeling. So it's a prototypical system for a lot of these really nice problems. You have an unsteady term. You also have a quadratic nonlinearity, so you have advective behavior, and you have an interesting linear term, a second order and a fourth order term, that if you actually choose different settings for the domain. So for example, over here, I've discretized my solution on 64 degrees of freedom, and I've specified the length of my domain to be minus pi to pi. If you change what equation 6 is, you get dramatically different behavior in your system. What do I mean by dramatically different behavior? You may get chaotic behavior, which is what we are interested in. You may get a steady state behavior, which means that your initial condition just dies out and you get basically a zero solution. So it's basically very interesting for many systems and how they and in nature. So we start with this. Another interesting point here is that we started off with looking at the system because data from the system is traditionally something that classical machine learning sequential techniques, for example, LSTMs, transformers, whatever you want to call it, struggle with intensely. So how, for example, can I ask questions to the audience just to sort of make it a little interactive? So for example, let's say that you're fitting an LSTM or a transformer to dynamical systems data. What loss function would you use? Mean squared error, right? Now in a chaotic system, would MSE be a good loss function? No, because mean squared error means nothing. Your dynamics could be absolutely pristine, but the trajectory will diverge because that is a hallmark of how the system is supposed to behave. So classical machine learning systems will not be able to predict this properly. Okay, they may work for stock markets. I don't know if they will work for stock markets. Don't quote me on that. Sorry. I've disabled my Robinhood notifications recently. So yeah. So but we want to. But what we want to do is we want to not use a mean squared error type okay, let me back up. I don't want to say that I don't want to use a mean squared error type of metric, but we want to tell our algorithm to learn the system that there's more to it than just a mean squared error. Okay, there's more to it than just saying minimize the difference between one trajectory and the other. Okay, but the mean squared error is important because in the short term you still want to match the trajectories, right? It's still a system which is deterministic for us. It's deterministic chaos. It's so it's a tricky problem, and it's a nice problem to look at, and we have some interesting results from this. Okay, so given this configuration, 64 degrees of freedom and a domain of -pi to pi, we want to learn how the system evolves using a neural OD. Okay, that's the problem statement. Okay, so of course we did do that, and as you can imagine, with the way I'm sort of phrasing this talk, it did not work, right? Which is why I'm here talking about what we did to try to make it work. The idea over here is to actually, again, try to leverage our understanding of the system and build a analog to a neural OD. It's still a neural OD that actually helps us preserve some property of the underlying system. Okay, so on the right hand side you have what I call the neural OD2, which is the neural OD that I introduced to you. That's basically finding the right hand side of the evolution of my PD, right? On the left I have pretty much the same thing, except that I have a linear nonlinear decomposition. Okay, I have a linear term that acts on the state and it's guaranteed to be linear, and I have another neural network which has its own set of trainable parameters, and it does its. Both these frameworks together on the same data set, which is data sampled from the attractor that I was talking about of the KS equations, and then we see what happens. We still use a mean squared error type of metric because the mean squared error is important for the short term, and then we see that, well, as you can tell, that the linear term makes a difference. Okay, so what is this linear term over here? So again, going back to numerical methods that some of us have a little bit of experience with, the linear term for a finite difference type of discretization needs to be symmetric. So you have a, if you remember how to calculate the second derivative on a grid, it's I+1 minus I-1 divided by 2 delta x. So similarly, we can constrain the A tilde term over here to have a banded structure where these pink squares all have the same number, right? So the linear term is the same everywhere because it's a uniform grid. We also tried some other tricks, for example, tricks from linear algebra to guarantee that it's symmetric and so on and so forth. We also embedded the periodic sort of boundary conditions that define this problem. And then when we train these two frameworks together, okay, we saw something interesting. So the first row is basically our true data, right? So we simulated the KS equations. We waited for the equations to hit a statistically steady state. So basically there is a behavior in the long-term limit that we observe when we go to the attractor. So the first column shows the short-term evolution of a test initial condition for 50 time units. The second column shows what happens once the system has been evolved for a very long duration. The first row, like I said, is data coming from a numerical method, so a finite difference step scheme. The second row is what happens when you use a regular neural OD, right? If you use an LSTM, it's even worse. So if you use a transform, it's even worse. So basically, this is probably the best we could do with a somewhat state-of-the-art architecture. What you'll notice is in the short term, if you just compare, again, I have more quantitative comparisons in a bit, but this is a good place to start. If you compare the first and the second rows from the top, you'll see in the short term, it doesn't look that off, right? So, but if you look at the second column, you'll see that the neural OD most times would blow up. It would just this sort of highway number sort of behavior would cause floating point overflow, right? The dreaded floating point overflow if you're doing fluid mechanics simulations. But we selected a case for which it did remain stable, just to show you how the blow up looked like. So you'd get these completely non-physical oscillations that show up. In comparison, the two rows at the bottom over here are where we have the linear term built into the neural OD, right? The first row, the third row from the top is one where we cheat. We know what the linear term for Ks is, right? It's the second order term and the fourth order term. So we just plug it in there. And we get a certain type of result. It's converged, right? And the second and the last row from the top is one in which we use the optimization to learn the linear term, right? And when we do this, well, we see that in the short term, again, I have more quantitative results in a bit. All of them are somewhat good, at least in the sense of the short-term forecasting. But in the long term, the presence of the linear term acts as a regularization, it's preventing us from blowing up. Okay. Okay, so this is good news so far. Yes, please go ahead.
Previous slide. So I think you have up in the top left this theta 3, but then it doesn't show up in the loss. So I think I'm just missing something.
Oh, sorry, the loss is only for the neural D1. So this loss is not shown over here. So these are two separate frameworks.
Oh, I see.
So this is the new neural OD we proposed, and the one on the right side is the one that's been around. So yeah.
Okay.
So the loss for this one would be everything the same, except it would just be f tilde theta 3u. Oh, that's it. Right. So it'd be a different loss. It's a different. Sorry if this slide was a little confusing. Yeah.
No, that's okay. And
Yeah.
the other thing I was curious about is you said the original system is chaotic, right?
Yes.
And so you're showing that you get the right kind of steady state statistical properties, but is the emulator chaotic in the same sense?
Yes. Yes. So we will see it in a while. Yeah. Okay. So these are the more quantitative results. So in the short term, again, if you pick a random slice of this, a random slice of the attractor state, and we evolve all these three emulators, so to speak, the regular neural OD, and the two neural ODs with the linear term specified by cheating and the linear term obtained by optimization. You see that, of course, when we exactly specify the linear term by cheating, there is a little improvement in the ensemble sense over the regular neural OD. But in general, you get this type of behavior with any numerical scheme. You get low error initially, and then as chaos kicks in, your error grows, and then it saturates. Okay. But what you see when you actually go into the attractor and you start bouncing around in this attractor is that you can plot these PDFs of the second derivative of the state and the first derivative of the state. On the top left, you have the PDF as it looks like for the true data, right, computed by a numerical method. And on the top right is what you get from a stable regular neural OD, right? So this is a neural OD that is bad. So this is the top right is basically the same simulation that I showed here, right? So it's you can see it's not that good. So that's why you don't get the right PDF showing up. So and is there a question online? No, sir. Okay. So, but what we want is this teardrop or pear-shaped attractor to show up as our emulators bouncing around on the attractor, right? It's not just about being stable. It's not just about capturing the L2 norm in the short term. It's also about capturing the statistic, which is, again, not something I built into the loss function, right? Right. It's fashionable to build your objectives into the loss function nowadays, right? We try to avoid that because you don't always know about these things, right? So, and you can see by specifying the linear term, you're able to get that density somewhat accurately. But there's something that we have actually achieved over here that is a little cooler, and that is the fact that at the end of the day, we have, by virtue of an optimization, we've actually learned this linear nonlinear decomposition of the right-hand side, right? And so if we actually now go back to, again, sorry, I'm much younger than the late 80s, but I do like reading papers from back then. So if you go back to this reference 9 over here, which is a paper from 1987 or 1988, this is a paper on something called approximate inertial manifolds. The idea is that if you have a dynamical system where you know what the linear term is, there exists for certain classes of systems a spectral gap in the linear term. So what does this mean? It means that if you do an eigen decomposition of the linear term, you actually get a separation of scales. So you have, so for example, if you do an SVD, right, on a matrix, you will see a separation of scales that shows up. If there is structure in your system, it's somewhat similar to that, except that this is something that is done on the discretized linear operator on the right-hand side of your PD. So for Kuromoto-Shevchenskiy, this is true. For Navier-Stokes, this is true. For Viscous-Burger, no. For the advection-dominated systems, such as the Burger's equation, this is not true. So, but what have we achieved here? Since we've actually learned what A is, okay, we can go in after the fact, after we have trained our surrogate model, and look at the eigenstructure of A to learn something about our system. Okay, so let's say that we've discovered what A is, and we've learned that A has a spectral gap, which for the Kuromoto-Shevchenskiy equations is true. We can actually do what I call flip the script, which is we can actually build a reduced order model of our emulator, so to speak. So the idea is that we built a neural OD that can sort of emulate our system, but if you were paying attention, you'd know that we are still looking at the original state of the system. So it was, 64 degrees of freedom. And of course, the fact that we don't have to do numerical solves of for example, spatial derivatives may give us a cost benefit. But what we also want to do is we want to reduce the memory footprint of our emulator, so to speak. So what we did over here was by leveraging approximate inertial manifold theory, we were actually able to identify a projection operator. So when you do an SVD, you can project onto the low dimensional singular vectors and obtain a reduced representation of your data, right? We do the same thing over here. We do an eigen decomposition of A. We compute the projection matrix using, is this by design or I don't know. Okay. Was something I said or? Okay. Right. So you do an eigen decomposition of A, you compute a projection operator, and then you can project your emulator, so to speak, onto a set of resolved and unresolved frequencies, or resolved and unresolved eigenvectors, right? So once you compute what P is through equation 11, you can execute equation 7, 8, which gives you two systems of equations. dP by dt is the resolved degrees of freedom, right? And Q is the unresolved degrees of freedom, right? So what we've done now is we've actually looked at our data. We've learned a system from the data. We looked at the linear term that fell out of the system, and we realized that we used way more firepower than was required. So we can kind of reduce the size of the system and make it more memory efficient by actually separating it into 2 degrees of freedom, P and Q, or 2 sets of degrees of freedom, and then ignoring what 8 is. Okay, so this is again a very classical technique in reduced order modeling, where the unresolved degrees of freedom in equation 8 are either ignored, right, or assumed to be stationary. So if you set dq by dt equal to 0, so 0 equals aq plus qf, whatever, then you can actually, by using one iteration of a linear system solve, you can represent q as a function of p as given in equation 9 and plug that back into equation 7, basically. Okay, so this is similar to what people call Galerkin reduced order modeling. This is also similar to what people call closure modeling for reduced order modeling. So, so there are a lot of things that resonate here with people who have been studying surrogate models for dynamical systems in the past. Okay. All right, so we've reduced our system from the entire state U to just the resolved variables P. So what does this do to our accuracy? So we looked at those PDFs I showed you in the chaotic steady state. So we can do a distance metric on PDFs given by the KL divergence. And you see 3 curves over here. So the orange boxes over here firstly, let me explain what's on the x-axis over here. So the x-axis is the dimensionality of P, so how many components we resolve. So as you know, if you do a SVD and you resolve more and more singular vectors, you get more and more accurate reconstructions of your data. So this is behavior that is expected, right? As we increase the degrees of freedom. In fact, for this particular problem, if you go beyond 18 degrees of freedom, you actually perfectly match the statistics of the original high fidelity model, which is a numerical solver, because the underlying dimensionality of the attractor for the Gromov-Krzyzewski equation is actually given by that value. So this is a nice confirmation of the fact that we are doing well. And so, okay, so the orange boxes over here are what happens if you basically set Q equal to 0. So when you set Q equal to 0, you get something called a Galerkin ROM, which, as you can see, as the values of P become lower and lower, you're basically missing a lot of information. So you get higher and higher errors in the sense of the KL divergence. In comparison, if you actually use equation 9 to correct equation 7, so you set Q equals A inverse capital QP, you get the blue circles over here. So you're able to sort of capture the effects of the unresolved scales. And the green crosses over here are something called, they call it post-processing Galerkin from the early 90s. The idea is for certain systems, such as the Gromov-Krzyzewski equation, you can actually solve the nonlinear Galerkin problem, which is you ignore what Q is, set Q equal to 0. And when you predict using this reduced system, you just remember what the values of P were. And after the fact, you apply that correction that I was talking about, the correction based on stationarity. And so you get something in between, right? So that's why you don't match the perfect perfect values of the blue circles, but you're able to get something in between. So again, but this is not a panacea. It's not going to work for every system, but for this system it did. So we looked at it, and so you can see the take home was that we had a system that was resolved on 64 degrees of freedom, and we were able to reduce our ultimate emulator or surrogate model or data-driven model to just 16 degrees of freedom. So 25% of its original size. We could have reduced it more, but we'd have to pay the penalty of a slightly higher error in the sense of our quantity of interest, which is the density at the steady state. Okay. So now the 64 degrees of freedom over here was just something that we chose, but how would this be useful to someone who is, for example, trying to learn a system from, say, satellite observations of the data? They have a resolution that's determined by their instrument, their measurement instrument. And by doing the analysis that we did, you can actually find, for example, a bunch of information. What is the underlying attractor dimension? Firstly, does an attractor exist, right? So is that spectral gap structured there in the linear matrix? If the attractor exists, what is its dimensionality? Can you do a further reduction of the system from, say, the instrument measurement to the attractor dimensionality? So there's a lot of things that you can do by following this particular process. And so this is somewhat starting to address, I don't want to say it has, this question of trying to extract some sort of structure, some sort of understanding from this surrogate that you're building. Yes, question in the audience.
So I have it right. It's what you're saying is that you can a priori use the eigenstructure, the process that you laid out in the previous slide, and some data.
For example, yes. Yeah. So, and I would say a posteriori, not a priori, because after training, you investigate the structure of A. So you train on the original state, but you deploy on the reduced state. So, okay. So it's moving more online cost offline. You see? Okay. Yeah, good question. Any other questions over here? Very quickly, question. These were all done for different initial conditions. So during the training, you can basically, so you have to give it sort of snapshots of trajectories. Let's say that is a hyperparameter. So you'd give it, say, 20 snapshots in time and ask it to train itself on the trajectory of 20 snapshots. So the initial condition could be whatever. So and in fact, we have examples, and the code that is there on the GitHub has different initial conditions as well. So you can yeah. So this generalizes to different initial conditions, but from the same system. That changes over the course of training, yes. Yeah. So we learn the structure of A. So these pink boxes, green boxes, and yellow boxes are all learnable parameters. It's actually 3 parameters over here. I call it learnable, but yeah. Yes. Question. Yes. Oh, okay. Thank you. Good point. Yeah. Very good question. So I've been found out by the audience. It's a smart audience. Yes. So the question is there a difference between the learned A and the fixed A? Yes, there is. And we actually have a trick that you can look up in the archive document to basically identify that the eigenvectors that fall out of the fixed A and the learned A are actually similar to each other given one transformation. So, okay, I'm going to go on a bit of a rant over here. Okay, but a lot of the data-driven approach to science is based on optimization, right? So you have non-Conway's optimization. So you frequently end up getting results that make no sense. Over here, I just had to learn 3 integers, right? -1, 2, +1, something like that, if it's a linear term. But the presence of this sort of complex type of optimization problem causes me to even suffer in that sense. So I can't even learn the linear terms in a finite difference stencil through this technique. So we had to do some additional sort of post-processing of the A term. But the idea was we were able to extract that spectral gap condition and the eigenvectors accurately as a result of that. So let's talk about that offline. Okay. All right. So yeah, all of these results, unfortunately, at the end of the day, are sort of limited by what is the optimization gap, right? So you must have heard about physics-informed neural networks. You must have heard about depot nets and Fourier neural operators. When you try them on very, very simple problems, which specific, how the weights of the neural network should be like, you still end up getting stunningly bad results. To give you an example, I was trying to learn an identity function using a 2-neuron neural network with 1 layer. So with a ReLU activation, I should know what the weights in the neural network should be. I mean, they should add up to 1 basically, and then give me the identity function. But when you put it into a stochastic gradient descent type optimizer, and you run 1,000 trials, about 80% of the times you don't get that exact weight to numerical precision, right? So some of these things that I'm trying to do are actually trying to bypass this problem that inevitably you'll end up hitting up against, right? So very good question. Okay, so let's move on. A question in the audience.
So to go back to the question, how do you make sure that the capital F term, the neural network part, also does not contain some linear component?
That's a good question. So the question is, how do we make sure that the F is purely nonlinear and the A is purely linear? We cannot at this moment, which is why we did that post-processing that we talked about in the previous question to ensure that we are able to get this sort of eigen decomposition that we desire. We tried a couple of things to ensure that F was purely nonlinear, but we don't have a satisfactory answer for that at the moment, right? That's a good question. So if anybody knows anything here in the audience about how you can learn a neural network, or you can train a neural network so that it cannot approximate a class of linear functions, I don't know. It can only approximate class of nonlinear functions? I don't know. I'm just brainstorming on stage. It's not a good idea. So, but yeah, that was a good question. So separating them perfectly to be linear and nonlinear, that is something that would be nice for us. Maybe that solves the problem and we retain the linear structure exactly every time once we do that. Okay, of A. Okay, so let's look at another example. I promise there'll be climate and weather examples shortly. I have 15 minutes left as well. Wow, I spoke a lot. Okay, so if we're going to look at another system over here which does not have that spectral gap condition. So this is a prototypical system for a lot of people who do turbulence modeling, which I did, which I have been doing in the past, and also for people who are doing advection dominated studies of advection dominated systems. So this system generates generates shocks or discontinuities. So you have smooth initial conditions which lead to discontinuous solutions. Again, very similar to the previous case, you have an unsteady term, you have a quadratic nonlinearity, and you have now a more conventional type of dissipative term given by the Laplacian. Some information about the domain. What is interesting over here is the choice of mu. Mu is the viscosity, which is taken to be a very, very small number, right? 8 into 10 power minus 4. So the system is basically having hyperbolic behavior. Okay, so it's very little dissipation. So that's why you have the presence of shocks. So to give you an example, we just run the same suite of analysis that we did in the past. The orange lines over here are the regular neural OD. The green and the red dotted lines are the neural OD with the linear term imposed on it, right? And you can see this is a mirror sort of replica of what happened in the previous case. The orange line, the regular neural OD, has all these high wave number, we call it Gibbs oscillations, is basically when a numerical scheme is not good enough. If we then do a couple more, we do a quantitative assessment of how the errors look like. So I have over here ensemble relative errors. So for, again, various initial conditions, there was a question about initial conditions, which, by the way, over here, the initial conditions were chosen as a superposition of sines and cosines. So it's basically, we have a random sampling of frequencies for our training and testing. And you can see that the neural OD basically goes up to 100% relative error very soon and basically keeps going. It may blow up also. So, but the linear terms, as you can see, if we cheat and specify the actual linear term, we get the best result, which makes sense because we've helped the ML algorithm a lot. The red dots are the situation where we learn what the linear term is, and so it's somewhere in between. Now, I said that this particular system is interesting because people use it for a lot of turbulence modeling analyses. So an interesting hallmark of the system is that it has a scale separation behavior, right? So the idea is if you look at the solutions of the system over time and you do a Fourier transform of the simulation and of the solution, and then you look at the angle average energy spectra in the wave number space. So it's basically a proxy for how much energy is contained in different scales. So the x-axis of these plots are wave number in space. You get the spectrum which shows a particular scaling behavior, k to the -2 scaling behavior. This is classic for what we call Berger's turbulence. So the k to the -2 in homogeneous isotropic turbulence, which is Navier-Stokes, you get k to the -5/3. So what people like to do is they like to test their schemes on this first before they go to the three-dimensional case. And as you can see over here, the orange curves are the results we get from the the nonlinear, the regular neural OD, which, as you can see, has this what we call pile-up error. So it's not able to dissipate energy properly because the linear term is not explicitly built into the right-hand side. Whereas the presence of the linear term actually dissipates the energy properly in the finer scales and is also able to match the tail of the spectrum over here quite nicely. So another validation of what this linear term is actually doing for us in this particular problem. Okay. Another test over here, this was mainly done to satisfy some program managers because they wanted to see how robust our method is for example, different initial conditions, but in the sense of adding a lot of noise. So the system, so the situation is something similar to training on data that was collected very pristinely, and then deployment on data which is coming from maybe a different instrument, which has a different sort of noise. And so over here, as you can see, the regular neural OD is not at all robust to noise. So if you add noise to a test initial condition and then evolve the system, you can't even see it. The orange line just blows up right away. Epsilon over here corresponds to the variance of the noise over here, and over here the linear terms, they stay bounded. And there's a plot over here that shows the same thing. Basically, no semblance of a spectrum that represents anything physically accurate coming from the neural OD, but the presence of the linear term is able to stabilize this. Okay. So there is this added benefit of robustness to noise. What more? So another experiment that we ran over here was to see what happens when our data itself is under-resolved. So in the previous case, we actually assumed that the observations of the Burger's equations were very finely resolved in both space and time. The idea is that our measurement apparatus is extremely costly, let's say, and then it's able to resolve in space very nicely. But in many practical scenarios, your measurements themselves are not very well resolved in space or time. And so this is an example where we actually, for a given viscosity, this is a slightly higher viscosity, we are able to again learn this system, but for a much coarser grid. So the original grid required 4096 degrees of freedom to evolve using a finite volume method, but we observed it by subsampling every nth data point. But even using this nth data point, we are able to, using these, for example, the red curves over here, the results from the neural network, we are able to learn the system. And what is interesting is if you then actually solve the system of equations, the Burger's equations on the coarse grid, you actually get a higher error. So not only does it learn the evolution of the system on the coarse grid, it also learns the stabilized evolution of the system on the coarse grid. So it's kind of able to learn the system as well as its closure because we are running it on a coarse grid. In comparison to the regular dynamics, which, like I said way back in the start, your regular dynamics may be given by a system of equations which are correct, but the degrees of freedom are not resolved enough to resolve, for example, to introduce a closure problem, for example. So over here, we learn the closure and the evolution of the system together by just observing it on a coarse grid. Okay, these two examples are cases where in the previous example, we generalized across initial conditions. Here we generalize across viscosities. So we measured systems from different initial conditions, but also different viscosities. So you can see that we are able to learn that evolution. Another viscosity where you have more discontinuous solutions. So this is good. And finally, I left it for the last 5 minutes, but I promised you there'd be something related to geoscience. So we took all these results and we said, okay, we're not going to be satisfied with them. We're going to try and apply them to a real world data set that's coming from a satellite and see if, see where the bread is buttered, so to speak. So we picked up this data set. This is still not the most difficult data set to work with. This is the NOAA optimal interpolation data set. It's collected from available. It has been collected from the 70s, but people generally use the data starting 1981, which is when satellites started getting really robust for observing these things. So this is the surface of the temperature on the surface of the sea resolved on a quarter-degree global grid, which we then subsample to have just a 1-degree resolution, which means that each snapshot for a particular day is 180 by 360. So it's 360 for longitude, 180 for latitude. So it becomes an image that you can then do a bunch of data analysis with. And then what we want to do is do precisely what we did for the past few examples, which were all one-dimensional problems. But here we want to learn the evolution of the state on a two-dimensional system. So we did that. And as you can see, we get similar results on the left. So what I'm showing over here, it's a little difficult to visualize a 2D grid. So I'm showing the first principal component of the 2D grid predictions from this method. By the way, these results are not published, but we're quite excited about that. On the left is a regular neural OD. So this is another classical behavior that you get from a lot of machine learning methods for time series data, which is it detects a spurious fixed point, or it detects a spurious steady state, which is not the real steady state because you've trained it on one-step predictions or five-step predictions, so it doesn't detect the long-term behavior. So the regular neural OD, basically initially it's somewhat capturing this frequency, but then it just loses the plot. On the right-hand side is the prediction from, this is just the first component, by the way. The right-hand side is the prediction from the neural OD that we proposed, which is again the linearization term is able to help us detect the right steady state. When we and that was similar for the other components as well. When we look at the behavior of the system by just putting down some probes in the Pacific Ocean. So for example, over here, we have a bunch of curves. Let me explain this to you. So the green curve is coming from a weather model that's run by the US Department of Defense. It's called HICOM. That model is run every 48 hours. So it gives you 2-day simulations of sea surface temperature, in addition to other things. The true data, the purple data is coming from the satellite data. So it's our test data, so to speak. The red curve is CESM, so it's the Community Earth System Ensemble Earth System model. So that was run in NCAR at Boulder. And I have specific details about computational costs slightly. What is interesting about CSM is that it's at the other end of the spectrum in terms of forecast. It was a 200-year forecast. So it's a climate model. HICOM is a weather model. So there's a difference between the weather and the climate. Okay. The light blue curve is coming from a regular neural OD. And you can see it's not able to capture the right frequency or the amplitude of the sea surface temperature at this particular point. I have more sort of ensemble results shortly. But in comparison, the neural OD that we pitched is able to capture at least the frequency, right? It messes the amplitude at a few places. If you look at root mean squared error metrics for these different methods, you will see that we actually end up beating the climate model that was run at NCAR. We somewhat are not as good as the weather model that was run on a much finer grid at HICOM. But you have to understand a couple of things over here. Our forecasts were done for 40 years. We just initialized the state of the environment in 2001, and then ran it for, on 1991, and we ran it for, 30 years, right? The CSM model was run for 200 years. So these are certain problems that you have with climate data. But the HICOM model was run every 48 weeks. So in some sense, the numbers that you get in the last row are not possible, in the truest sense, because you have to rerun a PD every 2 days to get a forecast for the next 2 days. So in essence, it should be not applicable, not applicable, not applicable, and so on, right? But I just store it here just to compare how a weather model does in terms of accuracy. And so the real sort of USP of this type of method is how much it costs for us to train it, right? So you'll see a lot of papers out there which do surrogate modeling, which talk about how long it takes to get a prediction at the end, which of course is going to be a good comparison because your neural network is trained. You just have to do a forward pass of your input and you get very good numbers. But I like to also put in the numbers required to train the method because those can be a significant figure. So it took 2 node hours. I don't know if it's actually 2 node hours. It was me emailing my grad student and him getting back to me in 2 hours. So it could be much less than 2 node hours. And he doesn't have a GPU because I didn't give him one. So so it took 2 hours, let's say, of compute time plus grad student time to get the neural OD ROM. These are numbers I picked up from the websites of HiCom and CSM. You can see they are run on high performance computing systems. And so they are much more costly, right? But one thing to remember for those who are not familiar with these types of models, you don't just get sea surface temperature with them. You get many things. You get other things, right? You get wind speeds, etc. So what I'm trying to say here is, I am not claiming that we should get rid of these 2 things. We don't need them anymore, right? I'm saying that what we have over here is a very, very good complement to these more traditional and definitely more interpretable and more reliable modeling strategies. For example, I'm currently working with a few geoscientists to take this neural OD reduced order model that we've constructed and use it as a boundary condition, right? So the way Earth system models are constructed in the DOE are that you have different modules. So you'll have a sea module, you'll have a land module, you'll have an air module. You can actually try to build emulators for some of these modules and interface them with the modules that you don't believe data science can do a good job with, right? So that introduces some issues with the interface conditions, and I do research on that topic as well. I'm not going to talk about that today, but this basically is the end of my first part. So thank you very much for your attention, and yeah. Okay, so again, thank you again for coming here. For, I guess, the few of you who decided to stick around after my first hour, I guess this is praise for me. Thank you. So the second part of my talk today is going to be very similar to the first, except that we're going to make assumptions about the nature of the system that we have observed data from. The assumption here is that our data is actually coming from a stochastic dynamical system. So, or a system for which there is a significant amount of measurement noise that needs to be accounted for in the dynamics that we learn. So, in some sense, this particular portion of the talk will be very similar to the first. It's going to mirror it. There'll be a few twists on the way. So this is work with Jonah and Yunnan, who are at Cornell University. Jonah was a phenomenal MSGI intern with me at Argonne, and with faculty and at IIT Chicago and Johns Hopkins. So this is credit to them. So we'll start with a little bit of a background into the types of systems that we are trying to learn. So the most general form of a stochastic dynamical system is shown in this particular slide. So if you remember in the second or third slide in the first portion of my talk, we basically use some terminology to show that you'd have a state that was evolved by a right-hand side, right? So that was the formulation of the neural OD. Over here, we have a system where you have, again, this is terminology that's used in the SD community, but the left-hand side of that equation 13 is basically an unsteady term. It's dx by dt. It's called dx because that's how they use it. The right-hand side is given not simply by deterministic evolution, but also a additive noise. Now, this is somewhat of a simplification. It's done to make the mathematics a little tractable. As you'll see, we want to use machine learning to overcome some of these restrictive assumptions. So what we have on the right-hand side of equation 13 is that mu term is called the drift, okay, and the sigma term is called the diffusion. So, and the capital B on the right-hand side, the dB, is a Brownian process. It's a sample from a Gaussian distribution. So what we have over here is a system that has a deterministic behavior in the ensemble sense, the mu, right? But it also has a stochastic behavior in an additive sense, right? So this type of system frequently is used to describe, for example, molecular dynamics. It's frequently used in what is called multi-scale modeling. So you'd have a stochastic system for particles, but you'd have a deterministic system for some quantity of interest, which is an integrated function of the particles, right? So, and you'll see in a moment that in equation 14 is exactly what I'm talking about. So you have a stochastic system given by 13. If it's given by 13, then you can actually write down a system in the density given those particles, right, by equation 14. So this is in the SD community, in some sense in the engineering community, this is known as the Fokker-Planck partial differential equation, which is a forecast nowadays. PDs are assumed to give us forecasts, but anyway, this is it solves for the time varying density, the probability, given evolution of particles of 13. So how would you visualize this? Let's say you take equation 13, you take a stochastic integrator, right, and you do Monte Carlo simulations. So you sample x at 0, t equal to 0 multiple times, and you push it through equation 13 for a certain time step, and then you histogram them. Let's say you get a density from the histogram. They should be similar to the solution you get from equation 14, given that the initial distribution you sampled from equation 13 is the initial condition of equation 14. Okay. In the statistic community, this is called the backward Kolmogorov equation. So I interviewed once for a job, and I said this is called the Fokker-Planck PD, and then a person got really mad at me. So I don't want anybody to be mad at me today. But the idea is that this type of sort of representation of a system 13 and 14 is very convenient for many, for example, modeling tasks in multiscale physics. So there's many things that you can model as particles, but at the end of the day, you care more about their continuum. We call it continuum properties, which are given by the density. So for example, a project I'm interested in, which I've put it down in a notepad of paper, but I haven't really, as usual, got the bandwidth to do anything about it, is do something like this for traffic flow, right? You have now what are called loop detectors, especially in California, where you have detectors for cars passing at certain points on the freeway over there, the interstate. So that could be your 13, right? And could you then use that to build a model for the density of the traffic in equation 14? And then potentially forecast how it changes over time. You don't care how individual cars are going to behave. You care how the overall traffic is going to behave, right? So that's something that should kind of make this a little more clear to you. But what you'll notice over here, as we move on to the next slide, is that as soon as you loosen assumptions about the nature of 16, things start getting a little hairy mathematically, okay? So let's say over here in 16 that in addition to a Brownian type of additive noise, I also have a Levy type of noise. So question for the audience, how many people know the difference between a Levy type of process and a Brownian process? Okay, does someone want to speak up then? No, they don't want to speak up, they know it, but because I was hoping you'd help me out, that's why. Okay, so let me look at the next slide first before we go back to the math on the first slide. So on the top row, you have something that is familiar to you. So you just sample from a Gaussian type process, and you add increments, and you get this type of behavior, which is, if you look at the range of the y-axis on all of these plots, you'll see that the system stays more or less bounded as you grow in time. It grows slowly. But in the Levy type of process, the easiest way to visualize this sort of qualitatively is you'll have Brownian type motion for large portions of time, and then you have these sudden jumps. So, and these sudden jumps are basically sometimes called flights, the Levy flights. And what is very interesting over here is that this type of process is now becoming very popular for modeling things like turbulence. I've talked about turbulence quite a lot, but phenomena which is inherently non-local, right? We have long-term effects or long-range effects which cause these jumps are something that are quite nicely modeled using the Levy process, but that's a little beyond our pay grade for today, so we leave it at that. What you need to take away from this is that if you have a right-hand side that gets more and more general, you start getting a Fokker-Planck equation that's more and more intractable. Okay, so if you looked at the previous slide, your Fokker-Planck equation was essentially this linear term in the density over here that showed up, and you had it was a linear PD essentially. But if you add a Levy term to equation 16, you have now a integral differential equation, which is that non-local nature of the additive noise that I was talking about. So over here, you have to then perform an integral with a certain measure. These are all the descriptions here. The details are not necessary. But what becomes difficult over here is how do you solve this equation as the state space grows? Okay, so Navier-Stokes, if you solve incompressible Navier-Stokes, you have how many variables? You have velocities, you have pressure. So it's in a three-dimensional case, you have four variables over here, and you have in a three-dimensional case, you have the Cartesian coordinates x, y, z. Over here, as the state space grows, as the size of your vector in equation 16 grows, your probability density function has to be solved in larger and larger hypercubes, so to speak. And the computation of this integral gets harder and harder as you go beyond dimensions of 4 and 5. So I think, again, literature review guys, always do it. My literature review tells me that, and correct me if I'm wrong, that this particular term has been computed numerically up to 4 dimensions. But again, the people who know about Levy process in the audience can correct me if they're wrong. That's what I found online. But the idea is that the takeaway is that this is difficult to solve numerically compared to the previous example. Okay, so the idea is, can we then, by observing these systems, these high-dimensional systems, can we avoid having to actually solve a Fokker-Planck type equation for which we don't really have a numerical method in the most general case, right? And there are some approaches out there which have started looking at that. Some people have, for example, the first example over here is what are called the neural SDEs. So if you've done literature review about neural ODs, you'd see that there's a lot of work in using stochastic differential equations as the forward model in a neural OD. In these papers, what they have done is they've unintentionally somewhat started solving the problem I just introduced. So they use an SDE where the mu and the sigma is parameterized by a neural network similar to a neural OD, and they try to find the forward model for a push forward from a Gaussian density to a target density. Anyway, if this does not make sense to you, ignore it. Just the idea is that they assume that the neural OD has a structure like 13. They assume that the neural network has a structure of 13, and mu and sigma are given by neural networks with trainable parameters. Okay. But that doesn't solve our equation because we don't want to impose that structure on our system, right? When we observe samples from a stochastic system, we don't know if it's purely, well, we can guess that it may be purely Brownian or otherwise, but we wouldn't like to constrain ourselves to that, right? So that's the limitation with that. The second example here is using some of the more modern architectures for computer vision, for example, generative adversarial networks. What this does is it looks at samples from, for example, the stochastic differential equation as samples from some unknown density, and then it just learns the sampler. Okay, it doesn't learn an explicit form of the density. The idea of a generative adversarial network is that it assumes that if you sample from a Gaussian and then you push it through some transformations that are learnable, you'll get a sample from your target system, which is useful for many cases. It makes videos and stuff like that. But for this particular case, again, what we want to do is we want to learn a dynamical system firstly, and secondly, the generative adversarial network. I don't know, does anybody have any experience with GANs in the audience? A little bit, yes. Have you ever felt like tearing your hair out when you try to train them? Yes, I also see some nods in the audience. I have myself. GANs are notoriously difficult to train, and not really much you can extract out of them mathematically. And since someone has done it, we decided to try something different. And then finally, you may be familiar with physics from neural networks. That's also from Dr. Karnidakis' group in Brown. What they have done in that particular scenario is they have tried to directly learn P as a function of X and T, right? And specified this equation as a loss function. In the case where they have to do something that is integral differential, they'll have, again, this as a loss function, but the loss function will require quadrature. So basically, they'll have to do a numerical discretization of their loss function every time they compute the residual for stochastic gradient descent. And that for various reasons was not very attractive to us. Because like I said, for many problems, the numerical discretization of this doesn't even exist. So, so we are trying to avoid that. Okay, so what did we use? So we decided to firstly, again, just go back and look at a few different papers in the past, and we saw that there's a rich body of work in optimal transport, so which looks to learn densities, right, or more appropriately learn maps between densities. And more recently, a close cousin of optimal transport, which is suboptimal in the sense of it's again using a non-convex optimization, is the normalizing flows, which as you can see over here, basically is tasked with learning a transformation from a known density to an unknown density, right? And the way it does this is that I'll get to that in a bit, but the idea is that if you are able to randomly choose a transformation at first and move a sample from a Gaussian to the target, you can compute the log likelihood of the difference between your actual observed data and what you got through the transformation to then improve what these transformations are, okay? And there is a specific structure to the transformations, right? There are some good properties about the normalizing flows that we can leverage for downstream tasks. That will become apparent in a moment. But we decided to go with this to see if, okay, given examples of these stochastic differential equations, can we, or samples from these stochastic differential equations, can we actually look at the samples but learn the time varying density, right? And then after that, can we look at the time varying density and back out something from the from that in the sense of knowledge about a equation? Okay, so this is a summary of what I just introduced. So the idea is that if X is your data, right? Again, we want to find a T of X to a sample from a Gaussian, which is given by Z over here. So P sub Z of Z, let me use my mounter, is a Gaussian distribution. So the idea is, what is my T? So in a normalizing flow, T is given by a series of transformations parameterized by neural networks. In some types of optimal transport is given by some triangular maps, but the overall thing you need to take away is that T has to be invertible. So there has to be a bijection between Z and X, and that both T and T inverse have to be differentiable. As long as you satisfy these properties, you can build a normalizing flow, essentially, okay? And how do you train what T is? You can use the law of conservation of probability to write down equation 20, which is that the the probability density of your target data, again, by virtue of the invertible nature of T, can be written as essentially this sort of volume preserving map on the right hand side. The J sub T over here is the Jacobian of T. So again, if you have a transformation T that is invertible, differentiable, and it's easy to compute the determinant of its Jacobian, right? You're in the, in the green. And so with 20, you can take a log of both sides of this equation, and basically the log likelihood of the left hand side has to be maximized, right? Or the minimum log likelihood has to be minimized. So you get a loss function like this. So the idea is, how do you train this? You take a sample from your target, your training data, you push it through a garbage T initially, right? The randomly initialized T. It goes and becomes a sample from a Gaussian. So log of the probability of a particle from a Gaussian is very easy to compute, right? You have a closed form solution for that, P sub Z. You can also compute the Jacobian of T. This is, again, you can use automatic differentiation, or many architectures actually have an analytical form of the Jacobian as a function of the neural network. So you'll see that in a while. And you compute the log of that, and basically that's the loss function with respect to one sample of X. Do this over multiple samples, do it again and again, take the gradient of this function with respect to the parameters in T, theta, and then you train your normalizing flow. Okay. What's nice about this particular formulation is that you can actually build complexity in a more modular manner. So for example, if you have two sets of transformations that are both invertible, you can basically compose them, and compose also their the determinants of their Jacobian to get more complex transformations. So you don't have to find one expression for T that hopefully works for you, but you could layer complexity. And so that is what generally people in the machine learning community are doing. And if you go out there and do a search for different forms of T, so different types of architectures, you'd find a lot of them. There's probably order of 50 papers which have looked at different architectures. They're all, but they're all essentially doing something like this. Okay, so now what is nice over here is that once you actually fit this architecture, you have an explicit way to compute the probability of a particular sample, right? So as against the generative adversarial network or other methods like projection pursuit, they learn the sampler. So they give you a neural network for which, if you sample from the Gaussian and push it through the neural network, you get a sample that's from the same density, hopefully, that you observed in your training data, but they don't tell you what the probability of that sample is. So over here, you actually get the explicit probability. That's a nice thing. It comes in use when you have to do things like parameter calibration and things like that. Okay. Anyhow, so let's look at, in my opinion, one of the simplest normalizing flow architectures that are out there, right? They can go arbitrarily complex. The idea over here is, again, like I said, build an invertible T that's differentiable. So one way to do this is to use something like an affine transform, which is also, so you can see it in equation 25 over here. So let's say my input to this transform is X. For the first D dimensions of X, so X has multiple, it's a vector, right? So it's got multiple scalars in it. So for the first D scalars, I do nothing. I just preserve what X is. But for D plus 1 to capital D, which is the rest of the state, I have this affine transform. So that becomes a function of the first small d scalars, okay? And you can easily see that this is very easily invertible. So in order to go back from Z to X, you subtract mu of Z, because Z1 to D, because that's exactly what, you didn't do anything to that. And you divide by e raised to mu, right? So it's invertible as well. Another thing is, if you were to compute the determinant of the Jacobian of this transformation, a little bit of linear algebra, you'd get a equation like 26, which again is very easy to evaluate. So an arbitrary invertible transform T it's most likely that the bottleneck for your transformation will be in equation 26, right? You specify maybe a very flexible transformation for equation 25, but the Jacobian of that transformation and then the determinant of that Jacobian will not scale well at all when the state increases, or it will not scale well at all. So it will not scale well when the state size increases. So this is something called the real NVP. That's the name of the architecture. It's also very, it's a paper that came out in 2016. It's very widely regarded. So over here, you may have noticed there's a couple of things that we added over here. So instead of having this neural network only depend on a particular value of the state at a particular time, so a particular subcomponent of the state, it also depends on the time itself, because at the end of the day, we want to learn a time varying density. So we also want to learn a time varying transformation. So the idea is this: my density evolves over time. Yes. So I want to learn a map from a known density, which in my case is a Gaussian, to a density which evolves over time. But my known density does not change. My known density remains a Gaussian with zero mean and unit standard deviation. But the transformation from that known density through my varying density changes with time. That's the idea, right? Instead of learning 20 different normalizing flows for 20 time steps, I learn one normalizing flow across the 20 time steps, and I can also interpolate because now it's a continuous function of time. Okay. All right, so let's look at an example over here. So this is a two-dimensional system. In this system, there is no Brownian noise over here on the right-hand side. So you have, so over here, these are two scalar equations. X1 and X2 are stacked together to give us the bold symbol X that we saw previously. There's a drift given by the term pre-multiplying dt over there. And there is a Levy process, additive Levy process given by L1 and L2, right? Some details about the hyperparameters for generating this training data set. Now, how does this system behave? So if you look at the top row, there's a very interesting behavior that you don't get in a sort of a Brownian type process. So over here, you start, you initialize the system with, again, like a Gaussian distribution that's centered at 0, but it has, it's got a certain range. It's between plus minus 2. And you see, as the system evolves on the top, it generates this multimodal type structure. You get the corners of the square basically at specific locations. And our idea is that can we replicate the behavior of this system of particles using a normalizing flow? So we have on the bottom samples from the normalizing flow as it learns this particular system. These snapshots that you're seeing over here are time instances for which we do not have training data. So we have, we take samples in time, and then we basically plot densities and samples from densities at times for which we did not have snapshots. So we are able to, do some sort of interpolation in time. So that's a good start. But this generic framework doesn't really have to be limited to the notion of time. So you may have, while messing around with these types of ideas, looked at the half moons data set, which is pre-packaged with scikit-learn. You pass a parameter to this function which generates this data set. And that parameter is basically noise. So how much noise you want added to the data set. So as you can see, you can parameterize one normalizing flow to actually learn various types of densities in just by incorporating that parameter into the transformation. So the transformation changes as the parameter changes. Again, these are for values that are not used in the training data set. Okay. Okay, why am I doing all this? So this is in some sense sort of uncharted territory. But the idea over here is that if you can actually find out what T of X or equivalently T inverse of Z is as parameterized by time, you can actually then use automatic differentiation to compute gradients of your flow map, right? with respect to spatial derivatives, with respect to the spatial coordinates, and also with respect to time. So the work that we are looking into right now is actually picking up these flow maps and then investigating, for example, how do these flow maps behave when we differentiate them with respect to time. And you'll see that there is structure that is present in them. And the idea is that can we use, again, certain techniques to learn the equations in these systems by investigating the structure, right? So this is in some sense work that is not completely finished, but I wanted to give you sort of an overlap of, sort of like an overlay of which direction we want to take learning stochastic dynamical systems for. The idea again is simple. We want particles to equations, but we want to, or maybe features of equations, but we don't want to specify exactly what they are a priori, because that limits us in terms of accuracy as well as computational cost. Okay, there's another use case over here. For example, let's say that now you in addition to something you wanted to do previously, which was learn the density over time, you also want to potentially reconstruct a partially observed system. So let me introduce some of this notation over here. So let's say that your system is again given by X, and you introduce a map called time delayed embedding, which basically takes some partial observables of X, which are given by psi over here. So the simplest example of psi would be, let's say that my X is 3-dimensional and I only observed the first component of the 3 dimensions. So psi of X would be X sub 0, okay? And I then take these partial observables of X for a period in history. So the map capital psi over here is basically taking partial observables of my state for different instances in time in the past, and then preserving it as a long state vector. The idea is that if you look at Taken's theorem for embedding, that there is a diffeomorphism. So again, an invertible transformation between the manifold that is spanned by the full state and the state in the partially observed coordinates, right? And our goal is to learn what this diffeomorphism is, but parameterize that diffeomorphism as a function of the time delay embedding. Okay, a lot of terminology and a lot of jargon over here. It'll be simplified, I promise. Okay, so the idea is we take what this capital psi is in equation 29, that becomes the conditioning factor of the normalizing flow. Remember, what is a normalizing flow? It learns a diffeomorphism. It just learns an invertible map. Over here, previously the map was parameterized by time. Now the map will be parameterized by this time delay embedding. Okay, and the idea is that through that we will be able to go from the partially observed state to the fully observed state. So we are going to do attractor reconstruction. Okay, so what does this algorithm look like? So again, the idea is that, let's see, over here we have some training data where we in the first line, let me use my mouse pointer over here. So in the first line, we will basically take our training data and generate some partial observables. Let's say we assume what the partial observable is. In this case, the partial observable is just a few components of the entire state, right? We will make some selections. These are hyperparameters for the embedding dimensions. So and the time delay. So the embedding dimension over here, what was the embedding dimension? So it is just again a hyperparameter that tells us how far back you want to go in time. And then we do something called noise inflated observations. The idea over here is that for certain deterministic systems, which we will see in a while, you can also use this method for doing attractor reconstruction with deterministic systems. But normalizing flows cannot learn singular densities. You remember it has to learn a flow map that is volume preserving. So if you have a density given by delta functions, essentially, this thing will fail. But there's an easy way to bypass that, which is you add some Gaussian noise to the delta functions and you get a density that you can then learn. Okay, so that's kind of what we do when we say noise inflated observations. Okay, so during the training process, we look at our full state and we say that we want a map from a Gaussian to the full state. Okay, we want a map from the Gaussian to the full state, which is parameterized by the time delay embedding. Okay, I'm going to take it very slow over here. Okay, map from the Gaussian to the full state, which is what we have been doing all this while, right? But instead of parameterized by time, it's parameterized by history. So it's, in a sense, non-Markovian, if you think of it that way, right? So if I've observed even partially a trajectory in the past, I can use that to find the full state in the present. Okay. Practically speaking, let's say I have a three-dimensional system. It's evolving in time, but I can only observe the first dimension of the system. For 10 time steps, I remembered the first dimension of the system only. That goes into my normalizing flow to predict the entire state at the 11th instant. Okay. So, but then again, I can still retain only the first dimension because that may be coming from an actual experimental measurement, right? So that's truth for us. And so if you are able to then train this phi over here, which is given by normalizing flow, you get results like so. So over here, again, this is the example of a singular density. If we solve Lorentz 63, which is like a canonical system, you will not get an attractor that looks like what you have on the top left. It's not going to be noisy. It's going to be like trajectories which are deterministic. So we cannot really learn a density which is given by essentially what is a delta function in phase space. So what we do is we add noise to this, right? And then what we are doing over here is we are only observing x. Okay, we are observing x in time, and we are preserving x for a certain amount of time in the past. And using that, we are learning a density of the entire state. Okay. So given the past, we learn a density of the present. We sample from this density multiple times, and we take the main value, and that's the black dashed line over here. The colored line under this under these black dashed lines are the truth, so-called truth. We only observe the blue line, right? That's the partial observable. And the black dashed line is the reconstruction from the normalizing flow. So we are able to see, even for, again, this is a chaotic type of system, we are able to get a reconstruction of, we call it attractor reconstruction. This is in deference to some literature that is already out there. But the idea is what we're doing is we're doing a subgrid reconstruction, or a reconstruction of terms that are not observed. So so that is another approach that you can use for this particular approach. What else? So I told you that our ultimate goal is to extend these methods to extracting, for example, the equations that are generating these state evolutions, and that's not a trivial task. And as you can see, the first parameterized neural network normalizing flow, we extracted some flow maps from that in the sense of gradients, but to go from that to a symbolic type of form is a long way to go, right? But we can leverage some literature out there for just the Brownian case. I understand that this is in some sense going back on my own words. I told you that we don't want to limit ourselves to just the Brownian case, and then I'm giving a Brownian example, sorry. But we have to start somewhere. So if you go to the reference over here, you will see that in the SD literature, there is if you have access to the actual underlying density, right, you can do a data-driven approach for computing what is called the generator of a particular function of the state. So X is our state, and F is a function that is applied on the state. At the moment, F is indeterminate. And what you can do is you can use this expression, which is nothing but the expectation of F at a certain incremental time into the future. Subtracted from F itself, you can discretize this on a particular mesh, X sub I, which is our high dimensional state space. And you can then estimate the generator. Why is this relevant? It'll become clear shortly. because for the case of the Brownian SD, there is a analytical form for the generator. Okay, so if you go through the derivations in 32 and 33, if you set f of x equal to just the identity function, you know that the generator of the of f of x equal to x gives you the drift. Okay, so we go back to this equation and we specify f of x to be just x. So this guy just becomes xi. The probability has come to us from the normalizing flow, right? We learned that already. So everything in 31 is now computable, right? This guy also just becomes x. You are able to recover the drift as a function of space. Okay. We still haven't extracted an expression for the drift. We have just recovered drift as a function of space. You go one step further. If you set f of x to be the square of the input, so x square, and assuming that you already calculated the drift from the previous time step, you are able to recover what is a sub ii, which is the diffusion of this particular system. And so let's say we then try this out for a particular type of system. We have for example, over here a one-dimensional double well system. So it's got a Brownian motion over here. It's got a drift given by this cubic and linear term. It's got a diffusion given by again a cubic term and a constant. And the interesting thing about the system is you can sample it on a uniform distribution initially, but then each sample ends up in one of two wells. So it's kind of similar to this system over here, where again, no matter where you sample, you end up in one of four wells, right? So, but this one, in this case, this is a Brownian type of process, okay? And so when we apply this data-driven estimation of the drift, how do we do? Well, we do well in the sense of getting something from just observations, right? So we are able to capture the trend of the learned drift. But as I said, this is work that is still underway, and you can see that there are certain errors at the boundaries which we are trying to diagnose as to why those errors are showing up and whether we can improve them in any way. If you look at the square diffusion, again, you see that we are able to capture the trend in the behavior of the diffusion. Now, what we are doing on top of this is doing something like sparse regression. There was a question about symbolic regression. But for simple systems like this, you could potentially try to learn the structure of these expressions by doing some sort of L1 type of minimization. So that's something that we are looking into. But you can see how just by virtue of learning this time parameterized density, or conditional normalizing flow is a more appropriate term, we're able to leverage tools that have been around for quite some time to extract certain knowledge about your system in a good way. Okay, so what are the applications of these types of things? So of course, as I said, if you look at the SD and the PD, or the SD and the Fokker-Planck equation, these are analogous to particle continuum coupling for many problems. So if you think about, for example, molecular dynamics codes and then their continuum counterparts, so there are applications of these types of modeling strategies over there. Of course, we talked about attractor reconstruction, which is again a subgrid modeling type of approach. And again, this is the last time I mentioned turbulence, I promise, but learning probabilistic systems is very important for situations where the boundary conditions of your simulations are given by, like a time varying density, for example, right? So in such cases, it's very difficult to specify closed form equations for your boundary conditions in simulations. But what we can do is we can learn densities for that instead and sample from the densities over time. But that introduces a different problem. The problem over there is that you have to satisfy certain properties of your physics, which I have not discussed over here. I have not discussed explicitly satisfying properties of your density. For example, an open question could be, let's say I sample a particle from my density, and that particle has to satisfy, or the ensemble of particles has to satisfy some property. right? I haven't built that into our formulation yet, but these are things that that are of interest to the community, broadly speaking. Okay, so I have 15 minutes left, but I'm going to stop here, and thank you all for listening. I did have plans to look at some code, but I totally understand if people are tired and just want to ask questions. But if they are interested, I can just quickly open up a Jupyter notebook and look at some coding together. Okay, how does that sound? Good. Okay, right. So we'll do that now. You can applaud me if you want. So, so okay. So again, let me pull up the. So unfortunately, so this talk is actually on my GitHub as the but for some reason from the wireless guest wireless over here doesn't let me push to my GitHub repository. Surprising. But I made some small updates to my talk, which I'll push the moment I go home today. So check tomorrow. So you can find the PDF of the talk here. Feel free to, so it's here. It's just from last night, not today morning. And so I have a couple of notebooks over here, which I think would be useful for everyone it's a starting point for some of the things that we've looked at. So we can quickly walk through this. So the first notebook is, yes, question?
Can you put that link in the chat?
Oh, sure, yeah. Let's do that. Can't find my Zoom.
Maybe somebody who's
Yeah. So as you can see, I was making commits to this at about 1 a.m. last night. So life of an academic, I guess. So okay, so there's basically two notebooks here. Each notebook corresponds to one part. The first notebook is some code that learns a neural OD, but in this case, this linear and nonlinear neural OD that I introduced. We can walk through it very quickly, but let me just give you a brief overview. I have 10 minutes. So, oh, I'm sorry. Yes. Better? Okay. Okay. So, so let's walk through this one at a time. So, the first cell is for imports, certain hyperparameters over here. So, I'm going to quickly go through these hyperparameters, but it's entirely likely to forget what I'm saying. So feel free to email me if you need to know more. What you have over here in the first line is batch time. So this is a question someone asked me in the break. This is the number of snapshots you show to your neural OD over time. So so you start at t equal to 0, go all the way to t equal to 19, compute the loss, and go back to t equal to 0. That's what 20 means over here. So this has to be less than the size of one of your simulations. So if you're sampling multiple simulations for your training data, this cannot be greater than that. The batch size is related to another question that was asked in the audience, that was different initial conditions. So 100 over here implies that you're going to take 100 initial conditions or 100 initializations of your neural OD and then evolve each of them for 20 time steps. So it could be from one simulation, could be from multiple simulations. It's just how you package your training data together. GPU is, in case you want to use a GPU, the adjoint mode over here is false. So if you remember, the neural OD can be trained in two ways. I only talked about the one way, which is adjoint equals true, which is you solve a forward problem to get the loss, and then you solve a backward problem, again, which is continuous in time, to get the gradient of the loss with respect to the parameters. The advantage of that is you have memory benefits, so you don't spend as much in memory to retain the intermediate time steps. So you don't have to save 20 intermediate predictions and compute the loss through that. If you set that equal to true, that's what you get, but you can set it equal to false and then just retain. If you have enough memory, you can retain all the 20 time steps and compute the loss like that. So over here, test frequency is just a hyperparameter for how frequently you want to check your. It's just a how frequently you want to check your performance of your training. And course deg over here is a hyperparameter for reducing the resolution of the training data. So training data is a little large, which, by the way, if you let's see, let me open this. There's a link in the README of the same. Yeah, so you can go to this particular, it's about a 500 megabyte data set. So you can download the data over here. Again, any questions, if you ask me any questions if you can't get it. And so the course deg over here, it takes the spatial solution of the PD and takes every 16th point. So it just makes training a little faster. I still recommend using a GPU for this. Anyhow, again, some basic imports. Okay, so this is the fun stuff. So over here, the OD func over here, this class is basically the right-hand side of our neural OD, right? So you can see the right-hand side has a self.net, which is basically the nonlinear term, right? So you remember I had a linear nonlinear decomposition. So this is the nonlinear term. And then you have something called the linear term over here, right? Which is merely a matrix, which is n by n, where n is the degree of freedom of your data set, okay? So as you can see, for this particular linear term, for this particular example, I kind of cheated and I put the exact linear term in there. So which was given by a viscosity of 10 to the negative 8 to the 10 to the negative 4 and a certain, so that the matrix entries in that diagonal are specified ahead of time. But in general, you could let this be trainable, right? This guy be trainable, and you could also learn the linear term at the same time. And what you could also do, which I have some other code for, but it's not in this repository, is also set other terms over here depending on your best guess about the underlying structure of the equation. So someone asked, can I specify for example, a higher order term? If you can write it down in this formulation, yes, you can. And then PyTorch just uses it as it. Okay, so that's a nice thing. Again, certain helper functions, not really very important. Certain plotting functions. Again, so you have data in a pickle format. So as you can see over here, the last dimension of the data is the spatial dimension. The middle dimension of the data is time, and the first dimension of data is the initial condition. So, or it's basically the simulation. So we just subsample in space to make training a little easier. This is the again function for performing the optimization of the neural OD. Nothing very fancy over here. Again, I would not recommend to do this on the CPU. And I don't know if you guys used to watch cooking shows when you were young. I used to. My mom and dad forced me to. Didn't learn how to cook though. You know, you would have people who would cook for you, and then they'd say, oh, but you know, we already have this dish prepared, so we don't have to wait while it's baking and stuff. So I have a pre-trained model in the repository that you can actually, sorry, wrong repository, that you can actually just use to mess around with different initial conditions. For example, one way that I would recommend you to play with this is to see what happens if you arbitrarily change the initial condition, right? At the end of the day, all these things are interpolating and they will eventually break. So it will be interesting to see how quickly you're able to break it. I suspect it'll be really quickly, right? So take the pre-trained model and see how it does. So over here, for example, these are testing initial conditions, again, superpositions of frequencies. And as you can see, the blue line is the truth and the yellow line is the prediction. So I trained this on Colab last night. What's interesting to see is that the discontinuity is picked up quite nicely. So if you're working in aerodynamics and you want to build reduced models of for example, flow around airplane wings, passenger airplane wings, then the location of this shock is very important. That has a very important role in how you want to design your aircraft, right? So it's good to see that these discontinuities are picked up, but also you see that certain subtleties, at least in this sort of 30-minute training that I did are not picked up. So this sort of wedge over here is not picked up. So this is for you to play around with. The second code I have, let's see. This was written by Jonah, again, my intern, so phenomenal grad student. So this uses a library called nflows. This is a very convenient library for learning normalizing flows. A lot of these transformations, such as the NVP that I talked about, and more state-of-the-art transformations that were published more recently, are all present in there for learning densities. So again, basic imports. We are going to look at the half moons data set over here. So again, half moons is available in scikit-learn, so it's kind of useful. So you see there's a noise parameter over here. If you increase this noise parameter, this guy gets more fuzzier, right? And so over here, what we have over here is this function. Again, feel free to ask me offline or through GitHub what the individual inputs to this function are. But instead of using that affine transformation, instead of using the triangular affine transformation that I talked about, it uses something called a neural spline flow, which is again another variant of a diffeomorphism that is more state of the art, so to speak, but it's built into nflow. So we went with that. And it chains two of these transformations together. So it takes two transformations, which are created by this function, chains this together. And as you can see, if you just train it for, this one will run on your CPU. So if you train it for just very little time, it's able to generate the half moons data set quite nicely. There are some outliers, of course, but you can mess around with the hyperparameters to change that. What we did is learn time varying densities. So the second example is maybe more interesting to you. Here we looked at the Lorenz 96 system. So this is not something I talked about today, but this system is nice because it lets you arbitrarily increase the dimensionality. So here it's 10 dimensional. Same thing. This is the time series integrator, as you can see. So this is the SDE, this line over here. So the W times numpy square root dt. You collect this data, and this is how this data looks like. So we just look at one of the observables, right, and sample it. So it's again also got a very complex type of density, as you can see. We go through this process of creating a transformation, but now the transformation has a conditioning factor, which is also time, but instead of just giving time as a direct input to the neural networks, we add an additional sort of embedding. So we push time through a neural network first before giving it directly to the map. And all in all, again, I'm racing through this a little because I'm out of time. The idea is that the flow is able to learn the evolution of this density quite nicely, even in high dimensional space, using this. So again, this work will go into a paper. So and this notebook is also much better documented. So I think you guys will enjoy yourselves over here. So yeah, thank you for your attention. And if you have any questions about these codes, feel free to try them out and shoot me an email. I'd be happy to discuss this with you. Yeah, thanks.